Alright, I'm going to work through setting up and solving this problem in line.exe. It's fairly similar to your homework problems and is fairly typical of what we'll be doing in the shafting section of the work here. So in this problem, it's simply supported just like your homework. We got one load at this gear center and then no load over here. So the loading is essentially the same but maybe a little simpler. Now before I get into the actual setup of the file, I just want to point out when you need nodes and when you don't need nodes. And you need nodes, let me zoom in here, anywhere you have a load or a boundary condition. So if I'm going to simply support it about the bearings, which are at the center of these X's, I'll need nodes there and there. And I'll also need one right here. I'm also going to put one at this gear center over here, even though I don't have any load indicated in this particular solution. I use this for a lot of different things, and the model I'm using has that set up, so I'm going to include that. So that's one thing. If you have a boundary condition, you need a node. If you have a load, you need a node. You can solve distributed loads in line.exe. It just takes a little bit more thought in the setup because you have to represent that distributed load as a bunch of point loads, and it's a little finicky how you do that. Now, the other time you have to have a node is when you have a change of geometry. So if I start at the actual start of the beam, which is over here, I'll need a node right there because we switch to the 1.3 inch diameter from the 1 inch. And then here we switch from the 1.3 to 1.75, and then go from 1.75 to 2.5, and so on and so on. I got a little heavy there, and like so. So if I count all these, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the minimum model to represent this beam in line.exe is 12 nodes. You always have one fewer elements than nodes, so that would be 11 elements. That's the minimum model. There are cases where you would want more nodes and elements than that, and we'll talk about that in a second. Now when you actually download the zip file, which contains line.exe, you'll get the executable. I think the Fortran file might still be in there. You don't need that for anything, and there will be an input file. And then there's several PDFs that are explanatory as well. I just want to work with the input file, and we're going to go to line_C here. The C is just for coarse, which means it's a minimum mesh. Coarse means very few elements and nodes. Fine would mean more elements and nodes. So when I open this, you can see my input file. See, I do have 12 nodes and 11 elements as mentioned previously. We got 4 sections and 1 material, 2 fixed points, and 1 load. If I go back to the PDF, zoom back out here. Let's talk about the sections real quick. You only need to define a section for unique geometry. So if you look at this just kind of at a glance, you've got 1, 2, 3, 4, 5, 6, 7 individual sections with their own diameter. But this 1 inch section over here on the left hand side can use the same section number as over on the right hand side. And same thing with 1.3 and 1.3. and 1.75 and 1.75. So what we really have here is we have 1 inch diameter sections, 1.3, 1.75, and 2.5. So we only need to define 4 sections. So that's what I have here. To input, I'm just going to kind of, well, let's just walk through the input file. Let's do that. You do have to have 2 comments, and they both begin with the word comment in lowercase, and you have a space, and then you can put anything you want after that. You probably want to keep the length of the comment to under 80 columns, which if you're in a text editor like Notepad++, which is free, it gives you the column length down here. As long as you keep that below 80, I know you won't have a problem. You might be able to go longer, but you shouldn't need to. I do recommend putting comments on here that explain what you're actually doing, because as you work through some of the homeworks you may end up with multiple input files for the same problem, and it just makes it easier to keep track of everything. Immediately after comments with no lines in between, you have materials defined with the word materials, plural, and then the number of materials, which in this case is all steel, so I'll only have 1. You got 1, which says it is material 1, and then the number next to that is your Young's modulus. And basically Young's modulus defines what units the rest of the problem is presented in. So 30 e to the 6, that's an approximate Young's modulus for steel in PSI. So that means all of my forces are going to be represented in pounds, and all of my length, which is in the nodal coordinates, is represented in inches. So in setting the Young's modulus, you're basically defining the problem. So your homework problem is in the SI units. In SI units, in this class at least, you always work with strength in megapascals, which since Young's modulus has units of strength, it also needs to be in megapascals, and it'd be about 207,000. Not 207 e to the 6. That would be, what would that be? I don't remember. Something else. It's 207,000 megapascals along with newtons and millimeters. For the sections, you can follow along here. Let me see real quick. The PDF that's included with the line.exe download has an example file that lists what all these are. I believe it's the cross-sectional area, which would be in inches squared. The moment of inertia in inches to the 4th. The half height of the section in inches. And this is a shear constant. You really only need to worry about the value of this if you are calculating transverse shear, or more to the point, if you care about the transverse shear calculation. But the correct value for a round beam is actually 4/3, or about 1.333. And that's actually true of the half height here as well. If you're not using the output of stress, then it actually doesn't really matter what values are in here, because those do not influence the deflection calculations. The only material property that influences deflection is the moment of inertia right here. So, as explained earlier, we need 4 sections to define this beam, 1 through 4, and then we've got all the properties attached there. Under that we have nodes. The node numbers are always going to count up consecutively rather. In this case 1 through 12. And then you have the x-coordinate followed by the y-coordinate. And since this is just a straight shaft, I'm drawing it in the x space. All of my y-coordinates are 0. And we're starting at 0 on the left-hand side, and then just putting in the coordinates of each node. Now looking back at the original drawing, we don't have, it's not just a running linear dimension from one end. That's actually a terrible way to dimension a shaft in general. This is a much more common way. But you need running dimensions from one end. So it might be useful, even in your initial setup, to just come in and write out the x-coordinates for all of these nodes. That tends to make it a lot easier to track mistakes in the going down the road. So I've got that set up. I end at 41, which, just as a quick check, this beam is 41 inches overall. The elements, what we're doing here, again, we've got the word elements, plural, followed by the number of elements, which in this case is 11. Those are numbered. The first number here is the number of the element itself, so that's element 1, 2, and so on. The next 2 numbers are what's known as nodal connectivity. Those indicate which nodes join, or which nodes are joined by element 1. So element 1 joins node 1 to node 2. Element 2 joins node 2 to node 3, and so on. And for a straight beam, it's always going to look just like this. In the second column, you'll have 1 through basically number of nodes minus 1. In the second column, you'll have 2 through the number of nodes. The fourth column here is the material number. We only have one material, so they're all defined as 1. And then the last column is the section number. So our first 2 elements are section 1, that's the 1-inch diameter. We've got 1 element at section 2, that's the 1.3, 2 elements at 3, and so on and so on. And you can see as we go towards the end and the beam starts to taper back down, we go back to 3, back to 2, and then back to 1, which is the 1-inch diameter portion. After that, we've got the fixity, that is the boundary conditions. This is a simply supported shaft, and again, going back to my figure, if I number the nodes on a drawing like this, and I'm working just with a mouse here, so it's not going to be too good. But if you number all the nodes ahead of time, then you can very quickly look and see, well, node 2 is at a support, so we need a boundary condition there. And I think, let's see, 1, 2, 3, 4, 5, 6, 7. It's also node 8 is the other boundary condition. And then the load, which is here, that's at node 1, 2, 3, node 5. So coming back to the file here, we got boundary conditions at 2 and 8. And here, that is, if it's a 0, that means it's not fixed in X. If it's a 1, that means it is fixed in X. Same thing here, but for the Y. Those are translations about X, Y, and then rotations about Z, that is planar rotations. So for simple supports, which is what's indicated here, you always have a pin joint, which removes both translations, and you always have a roller joint, which removes the perpendicular translation, which is the Y direction here. And lastly, we had one load being applied, which is 500 pounds acting downward. And this uses the sign convention of positive upward, so we have a negative sign thrown in there. And then lastly, you do have to have a blank line at the end of the file. That's what the reader, which is coded into the Fortran itself, needs that black line or blank line to know that it's done. If you don't have that, you will get an error when you go to run it. Now to run this line file is line_c.inp. Make sure you save the file after you do any editing. And to run it, you're just double clicking the executable. And then you need the full name of the file, including the extension, which is .inp. If you've never turned on the extension view in Windows, you probably want to do that when you're working with this problem. And to do that, just open any Explorer window, go to Organize, let's see, Folder and Search Options, View, and then somewhere under here, right there, this is probably turned on by default, hide extensions for known file types. Make sure to turn that off, and that way in your browser you see INP, OUT, and that sort of thing. So that's my input file. You can name the output file anything you want. I always just use INP and OUT, or sometimes I use I and O for the extensions, but I usually give the file name the same for both of them. I'm giving it a 2 here because I've already solved this and I don't want to overwrite my file. If it runs completely and correctly, you're going to see this exact message here, which echo incomplete followed by there is no need to save and after IO is closed. So if you see that, everything worked fine. Before we talk about results, let's see what it looks like when everything does not work fine. So I'm going to introduce an error into this, and I'll tell you one of the most common errors that happens is there's a mismatch between the number of elements or nodes or load points, etc. that should be there and the number that actually are. So right now it's looking for 12 elements, but I have only 11 defined. So if I save this and run it again, you can see I got a runtime error, illegal character. This is all somewhat nonsensical to you, I would expect, unless you've worked with Fortran before. But what it does show you very clearly is where it had a problem. And if you scroll up here, you can see it's reading the elements, and after reading the 11th element, it had a problem. And right there you can see, again, we got 12 and we have 11. So you know there's a mismatch. Fix it, and you're all good. So that's the basic setup and how to run the thing. In terms of interpreting the results, we need to look at the output file. So I've got line_c.out. It's just another text file. And the first big part of it is just echoing the input deck. So even if you didn't have the input deck for this model, you would still know exactly what went into the results. It's got all the fixity here. It's got the loading, which we only had one load. And it's got the nodal coordinates, it's got the element numbers, it's got the section numbers. So you could recreate the model in full just from this information if you needed to. Now what we're interested in this homework problem is only the displacements. So immediately after the echo of the input data, we get displacements and global coordinates. This is where we're interested. We also get some forces, including shear and moment, and we get some stresses. In this problem, we're not interested in those values, but they are there. So we've got Y displacements and Z rotation. So in terms of the homework, you're asked about displacements at the load point. So in our case, the load point is 5. So if I look at node 5 right here, the nodal displacement is 0.033925 inches. This is a numerical program, so it'll give you as many units as you want, but in reality I'd call that 0.339. You don't want to just carry a bunch of units for no reason. And the other thing asked for in the homework was slopes at bearings. So looking back at the problem, we've got a bearing at 2 and we've got a bearing at 8. That's where we're interested in the slope, and slope in this case is what's referred to here as a Z rotation, and that's in radians. So you can see at bearing 2 we've got a slope of about 0.003 radians, or excuse me, 0.045 radians in the negative direction, and then down here we've got about 0.025 radians. And that is essentially it relative to your current homework. Now I'm going to carry this just a little bit farther. If you're not interested in reading ahead, you can skip out here. But I do want to kind of interpret these results a little bit farther, because as stated, this setup was for a minimal model. It's where you have to have a node at a load point, you have to have a node at a boundary condition, and you have to have a node at a change in geometry. And if we look at that minimal model, and all I've got here is I've copied in the y displacements, the slopes, the shear, the moment. No stress data, but you know, if your forces are right, your stresses are right. So if I look at these in these plots, the sort of orangish color is a fine model with a lot more nodes and elements. You can see here I've got actually, I think it's 41 or 42 nodes. But anyway, looking at the model that I just showed you, which is the minimal model, we've got a shear moment diagram that looks like that. And if I turn on the data for the much more refined model, they look identical. It's because forces are not particularly dependent on mesh refinement, which means that a very coarse model does a good job of capturing the shear and the moment. So that's not bad. However, if we look at slope and displacement, it tells a very different story. So again, I'm going to get rid of the fine models and show the slope and displacement. Now what should stand out to you immediately about this is both slope and displacement have to be continuous functions. If they're not continuous, that indicates basically the shaft is bent, which is not something that a linear calculation can capture. So in this case, neither one of these is showing particularly good data. However, I'm going to turn the refined information back on, and let's just zoom in on displacement here. Those markers are making it kind of hard to see, but what actually is, let's see if I can do this real quick. That's a little easier to see. In between the nodes, this coarse model, which is the blue, does a horrible job of showing what the actual displacement looks like. But anywhere you have a node, it's right on the money. It's because the node itself captures second order behavior, which is what displacement is, but it just can't interpolate in between. So you're only getting data out where you have a node point. So by creating a bunch more nodes, which is the fine model, I get a nice continuous function. But if all I care about is displacement at bearings, or slopes at bearings, displacement at gears, and things like that, well then I don't need all that information in between. And in fact, if I turn this data off again, get rid of that, this is the node that captures the slope at the first bearing. This is the second bearing. This is displacement at the gear. If I turn that back on again, they're exactly lined up and identical. In fact, if you look at the numeric value between the coarse and the fine model, it is genuinely the exact same value, so it makes no difference. So in this homework, you're asked only about some deflections and some slopes, which means a coarse model is perfectly adequate to capture it.